Products of generating functions. Our example in the previous subsection showed how to use generating function to turn a recurrence relation into an explicit formula. However, they only contained one generating function. Time has come for us to learn about the combinatorial use of the product of several generating functions. Lemma 8.4. Let an braces with n which is greater than equals to 0 and bn braces with n which is greater than equals to 0 be two sequences, and let a of x equals to the summations of an times x to the n summing for all n which is greater than equals to 0, and b of x equals to the summations of bn times x to the n summing for all n which is greater than equals to 0 be their respective generating functions. Define Cn which is equals to summations of ai times bn minus I, summing with the index starting from 0 to n, and let C of x is equals to the summations of Cn times x to the n, summing with n which is greater than equals to 0. Then A of x times B of x is equals to C of x. In other words, the coefficient of x to the n in A of x times B of x is Cn, which is equals to the summations of ai times bn minus I, summing with index I starting from 0 to n. Proof: when we multiply the infinite sum A of x equals to a0 plus a1x plus a2x squared and so on, and the sum b of x equals to b0 plus b1x plus b2x squared and so on, we multiply each term of the first sum by each term of the second sum, then add all these products. So a typical product is of the form ai times x to the I times bj times x to the j. The exponent of x in this product will be n, even only if j is equal to n minus I, and the claim follows. The combinatorial consequence of lemma 8.4 is the following theorem. Theorem 8.5. The product formula. Let An be the number of ways to build a certain structure on an n-element set, and let Bn be the number of ways to build another structure on an n-element set. Let Cn be the number of ways to separate n into the intervals S equals to the set 1 to 3 until I, and T equals to the set I plus 1, I plus 2, and so on until n. The intervals S and T are allowed to be empty. Then, to build a structure of the first kind on S, and a structure of the second kind on T. Let A of x, B of x, and C of x be the respective generating functions of the sequence A braces, B braces, and C braces. Then A of x times B of x is equals to C of x. Proof: there are ai ways to build a structure of the first kind on S, and bn minus I ways to build a structure of the second kind on T. This is true for all I as long as 0 which is less than equals to I less than equals to n. Therefore, Cn is equals to summations of ai times bn minus I, summing with I starting from 0 to n, and our claim follows from lemma 8.6. Example 8.6. Our claim follows from lemma 8.4. Example 8.6. A semester at a technical university consists of n days. At the beginning of each semester, the DN of engineering designs the term in the following way. She splits the term into two parts. The first k days of the term will form the theoretical part of the semester, and the second n minus k day will form the laboratory part. Here, 1 less than equals to k less than equals to n minus 2. Then she chooses one holiday in the first part and 2 holidays in the second part. In how many different ways can she design the term with these constraints? Solution: let Fn be the number of ways the Dn can plan the semester. It is straightforward to see that Fn is equals to the summations of k times n minus k choose 2, summing with a k starting from 1 to n minus 2. Looking at this expression, however, it is not so easy to see if it has a closed form. That is a form without a summing sign. And if it does, what it is. Let us separate problems of finding holidays in the two parts of the semester. There are k ways to do it in the first part, and m choose 2 ways to do it in the second part, where m is equal to n minus k. The generating functions of these two sequences are a of x equals to the summations of k times x to the k, summing for k which is greater than or equals to 1, and b of x is equals to the summations of m choose 2 times x to the m, summing for all m which is greater than or equals to 2. Recall from calculus that the summations of x to the I summing with I which is greater than or equals to 0 is equals to 1 divided by 1 minus x. Taking derivatives, this implies that a of x is equals to x divided by 1 minus x to the square, and b of x is equals to x squared divided by 1 minus x to the cube. Now let f of x be the generating function of the sequence if n braces. Then a of x times b of x is equals to f of x. Therefore, f of x is equals to a of x times b of x, which is equals to x to the cube divided by 1 minus x to the fifth, which is equals to x to the cube times the summations of n plus 4 choose 4 times x to the n, summing with n which is greater than or equals to 0, which is equals to the summations of n plus 1 choose 4 times x to the n, summing with all n which is greater than or equals to 3. And this shows that fn is equals to n plus 1 choose 4. Example 8.7. Now assume that instead of holidays, the DN chooses some days for independent study in both parts of the semester. In how many different ways can she plan the semester with these constraints? Solution. Let Gn be the number of ways the DN can complete this task. Again, let us split the problem into two parts. Let C of x be the generating function for the number of ways to pick a set of days for independent study in the first part. As a k-element set has 2 to the k subsets, we have C of x is equals to the summations of 2 to the k times x to the k, summing for all k which is greater than or equals to 0, which is equals to 1 divided by 1 minus 2x. Clearly, the second part has the same generating function, as our task is the same. Therefore, we get f of x is equals to c of x times c of x, which is equals to 1 divided by 1 minus 2x squared. This shows that f of x is equals to 1/2 times c prime of x. Therefore, f of x is equals to 1/2 times the summations of n times 2 to the n times x to the n minus 1, summing with all n which is greater than or equals to 1, and which is equals to the summations of n plus 1 times 2 to the n times x to the n, summing with n which is greater than or equals to 0. Showing that Gn is equals to n plus 1 times 2 to the n. A little thought shows that theorem 8.5 can easily be generalized from two generating functions into any fixed number of generating functions. The following example is an application of this generalized product formula. Example 8.8. Find the number of ways to split an n-day semester into 3 parts. Choose any number of holidays in the first part, an odd number of holidays in the second part, and an even number of holidays in the third part. Solution. Let Gn be the number of days, the number of ways the one can plan such a semester. Let a of x, b of x, and c of x be the generating functions for the sequences for the 3 individual tasks. That is, a of x is equals to the summations of 2 to the n times x to the n, summing with O n which is greater than or equals to 0, which is equals to 1 divided by 1 minus 2x. Since there are 2 to the n ways to choose an unspecified number of holidays from a set of n days. And as we have seen from chapter 3, the number of subsets of n braces that are of odd size is 2 to the n minus 1 if n is greater than or equals to 0, and 0 if n is equals to 0. Therefore, b of x is equals to the summations of 2 to the n minus 1 times x to the n, summing for all n which is greater than or equals to 1, which is equals to x divided by 1 minus 2x. Finally, the reader is asked to prove that the number of subsets of n braces that are of even size is 2 to the n minus 1 if n is greater than or equals to 1, and 1 if n is equals to 0. Therefore, c of x is equals to 1 plus x divided by 1 minus 2x, which is equals to 1 minus 2x divided by 1 minus x divided by 1 minus 2x. Now let g of x be the generating function of the sequence Gn braces. Then g of x is equals to a of x times b of x times c of x. Therefore, g of x is equals to a of x times b of x times c of x, which is equals to 1 divided by 1 minus 2x times x divided by 1 minus 2x times 1 minus 3x divided by 1 minus 2x, which is equals to x times 1 minus 3x divided by 1 minus 2x to the cube. The partial fraction decomposition leads to the equation g of x equals to minus 1 divided by 4 times 1 divided by 1 minus 2x plus 1 divided by 4 times 1 divided by 1 minus 2x to the cube. Finally, using the binomial theorem, we get that 1 minus 2x to the minus 3 is equal to the summations of minus 3 choose n times minus 2x to the n, summing for all n which is greater than or equals to 0, which is equals to the summations of n plus 2 choose 2 times 2 to the n times x to the n, summing with all n which is greater than or equals to 0. Therefore, g of x is equals to minus 1 divided by 4 times the summations of x to the n, summing with all n which is greater than or equals to 0, plus 1 divided by 4 times the summations of n plus 2 choose 2 times 2 to the n times x to the n, summing with all n which is greater than or equals to 0. So Gn is n plus 2 choose 2 times 2n minus 2 to the times 2 to the n minus 2 to the n, then divided by 4, which is equals to 2 to the n minus 3 times n plus 3 for n which is greater than or equals to 0. Example 8.9. If p less than or equals to k of n denotes the number of partitions of the integer n into parts of satisfies at most k. Then the summations of p less than equals to k of n times x to the n summing with O n which is greater than equals to 0, which is equals to the multiplications of 1 divided by 1 minus x to the I, where the multiplication is taken among all indexes I starting from 1 to k, then which is equals to 1 plus x squared plus x cubed and so on, times 1 plus x squared plus x to the 4th plus x to the 6th plus so on, and times so on until the general form 1 plus x to the k times x to the 1 plus x to the k plus x to the 2k plus x to the 3k and so on. Solution. Let us determine the coefficient of x to the n on the right hand side. The right hand side is a sum of k member products such that each member comes from a different parenthesis. The member from the ith parenthesis is of the form x to the I, j, I, and the sum of the exponents of the k members is n. In other words, 1 j1 plus 2 j2 plus 3 j3 and so on plus k jk is equals to n. If we write 1 plus 1 plus 1 and so on plus 1, j1 copies of 1 instead of 1 j1. And in general, I plus I plus I plus I and so on, ji copies of I instead of I ji. In the previous equation, we obtained a partition of n into the sum of parts that are at most k. Using this procedure, each time a product on the right-hand side is equal to x to the n, we obtain a partition of n into the sum of parts that are at most k. Conversely, each partition of n into parts at most k can be associated to a product on the right-hand side, and the statement follows. We proved in chapter 5 that p less than equals to k of n is also the number of partitions of n into at most k parts. Thus, the multiplications of 1 divided by 1 minus x to the I, where the multiplications it is taken among I starting from 1 to k, is also the generating function of those partitions. You could ask what the use of all this is if the above generating function does not yield a particularly nice closed formula for the numbers p less than equals to k of n. The quick answer is that any mathematics software can provide the expansion of 8.11 up to several dozen terms, so 8.11 provides a painless way to obtain a lot of numerical data. A much deeper answer, and we will see examples of that soon, is that the generating function of a sequence contains a lot of information about the sequence, sometimes even more than an exact formula. Example 8.10. If p of n denotes the number of partitions of the integer n, then the multiplications of the summations of pn times x to the n summing with n which is greater than or equals to 0, which is equals to the multiplications of 1 divided by 1 minus x to the k, where the multiplication starting from 1 to infinity, which is equals to 1 plus x squared plus x to the cube plus and so on. This is the first term with braces, times the second term with braces, 1 plus x to the x squared plus x to the 4th plus x to the 6th and so on, times the third term with braces, 1 plus x to the cube plus x to the 6th plus x to the 9th, and so on, and so on. Solution. Same as the proof of the previous example, just here there is no limit on the size of the parts, and therefore there are infinitely many parentheses on the right-hand side. The reader may think that such a generating function that is the infinite product of sums is not very useful. Indeed, a computer would have a hard time to handle an infinite formula. The following example disproves that belief. It is a stunning example of a problem that is much easier to handle with the generating functions than without them. Example 8.11. The number p odd of n of partitions of n into odd parts is equal to the number pd of n of partitions of n into all distinct parts. Solution. The crucial idea is this. It suffices to show that the generating functions of the two sequences are equal. It is clear that the f of x is equals to the summations of p odd of n times x to the n summing with all n which is greater than or equals to 0, which is equals to the multiplications of 1 divided by 1 minus x to the I, where the multiplication is taken among all I which is greater than or equals to 0 and the I is odd. And g of x is equals to the summations of the generating function is equals to the summations of pd of n times x to the n summing for all n which is greater than or equals to 0, which is equals to the multiplications of 1 plus x to the I multiplication is taken among all I which is greater than or equals to 1, which is equals to the multiplications of 1 minus x to the 2i divided by 1 minus x to the I, where the multiplication is taken among all I which is greater than or equals to 1. Note that after cancellations, the denominator of g of x will contain 1 minus x to the I, even only if I is odd, and will therefore be the same as the denominator of f of x. As both numerators are equal to 1, the proof follows.